Hello students, welcome back to my channel. We are so glad to see you here. Stay tuned for more exciting content and feel free to engage with us in the comments or share your thoughts. I hope your JEE preparation is going fantastic and you are also revising the content periodically. Consistent revision is the key to solidifying your understanding and boosting your confidence. Keep up the hard work, stay focused, and remember, every beat of effort brings you closer to your goal. Today we are going to start with 7th class on permutation and combination. And today's content is all about grouping of objects which are distinct and alike, distribution of groups, and integral solution of equations. Don't forget to subscribe, like, and share the content with others. Your support helps us grow and bring you more amazing content like this. Stay tuned and let's keep the learning going. Let's dive right into today's topic. Thanks once again for joining us. So today we are going to start our class with grouping of objects. And here, whatever we will discuss is all distinct objects. If nothing is said in the question, you will treat that thing, the objects, to be distinct. But if the objects are identical, you will definitely get that instruction in the question. So in this case, whatever we are considering now and whatever we are discussing now is grouping of objects which are all distinct. And at the same time, we will learn how to distribute these groups. We are going to discuss grouping of objects and distribution of objects simultaneously, so that we can understand the fact in a better way. Now see, suppose I have been given there are 5 distinct objects. Let us say these objects are A, B, C, D and E. Now if I ask to form a group of 2 objects and 4 and 3 objects. I want to form 2 groups. One group will have 2 objects, another group will have 3 objects. Now before starting with grouping of objects, you must remember one thing, that grouping is all about selection. You are selecting the objects for the group you are being given to construct. Is it clear? So grouping is always selection. Now these 2 objects can be selected from these 5 distinct objects in 5C2 different ways. And now after selecting 2 objects, we are left with 3 objects. Now that 3 can be selected in 3C3 different ways, that is in only one way. Is it clear? So this is the total number of ways in which you can form 2 groups which will have 2 objects in one group and 3 objects in the other group. Now, if I go for calculating this, what we are going to have? We are going to have factorial 5 divided by factorial 2 into factorial 3, and 3C3 is basically 1. So actually we are having factorial 5 divided by factorial 2 into factorial 3. Is it clear? So this is the total number of ways of forming these 2 groups which are having 2 and 3 objects. Is it clear? Is this clear to everyone? Now, my question is, in this problem, does your order matters? What is the question? Does your order matters? That is, in forming the group, does the order matters? That is, in this case, first I have selected 2 objects, then I have selected 3 objects, right? But now if I reverse our selection, that is, if I first choose 3 objects, then that can be done in 5C3 different ways, and the remaining 2 objects can be selected in 2C2 different ways. So my question is, does this order and this order same or they are different? So let me just calculate this. 5C3 is what? It is factorial 5 divided by factorial 3 into factorial 2, and 2C2 is again 1. So we are having factorial 5 divided by factorial 3 into factorial 2. Now see, this one and this one, they are not different. They are exactly same. So what we have learned, what conclusion we have drawn? That is, in case of grouping, the order does not matter. In which order you are selecting the objects, it does not matter. So keep this thing in mind. Now the next question is, if we do it by this, using this C, then there is no problem, we have done this. But my question is, can we write this answer directly? When we have been given 5 distinct objects, and out of that you are making 2 groups of 2 and 3 objects, can we write this answer directly? Yes, we can. If you see, if you observe carefully, you will find that we have been given 5 distinct objects. So in the numerator I have written factorial 5. And in the denominator what I have written is, you have formed 2 groups containing 2 objects and 3 objects. So what I have done, I have simply divided by factorial 2 and divided by factorial 3. Is this clear or not? Okay, it will be clear if I take some more examples on this. See this question. In how many different ways 10 objects be grouped into groups of 4 and 6 objects? Now if I use my C method, we are actually using C, but directly if we use C, that is the combination 1, what you will say? First I am selecting, because grouping is same as selection. First I am selecting 4 objects. As order does not matter, so you can select 4 first then 6, or you can select 6 first then 4, all same. So from 10 objects, 4 objects can be selected in how many different ways? 10C4 different ways. And we are now left with 6 objects. So that can be selected in 6C6 different ways. Therefore, total number of ways will be factorial 10 divided by factorial 4 into factorial 6 into 1. So we got this thing like factorial 10 divided by factorial 4 into factorial 6. Am I correct or not? You see, if I use C, we are getting this, right, as your answer of dividing this 10 objects in 2 groups containing 4 objects and 6 objects. Now you can write this answer directly, as I told you right now. There are 10 objects, so you will simply write it is factorial 10 divided by, it has been divided into 2 groups containing 4 and 6 objects. So it will be divided by factorial 4 and by factorial 6. That's it. That's exactly what we got. Is it clear? So whenever they are asking for grouping, we are always going for selection, And we can do this in two ways, actually in one way, which can be written in two ways. One, if I do it directly by C. So first I am choosing the first group. In this case, 4 objects to be selected for the first group. So it is 10C4. And for the second group, you are selecting, because we are left with 6 objects, that 6 objects can be selected in 6C6 different ways. This is one way of doing. Now, after simplifying this combination C, we got that whatever answer we are getting, we can write that directly. How? First, we have to see how many objects are to be grouped. So in the numerator, you write down factorial of that. In this case, we have written factorial 10 in the numerator. And we are dividing it in two groups of 4 and 6 objects. So I have divided it by factorial 4 and factorial 6. That's it. Let me take another problem. In how many different ways a pack of 52 cards can be grouped into groups of 7, 10, 15 and 20 cards? So if I go by C method, first I will write 52C7. Again, I am telling you, order does not matter in case of grouping. So I can select any, objects from any group. I'm selecting the first group, which will have 7 cards. You can start with 10, you can start with 15, you can start with 20, doesn't matter. So 52C7 is the number of ways of selecting 7 cards out of this 52 cards. So one group is formed. Now, we are now left with 45 cards. Out of that 45 cards, I am selecting 10 cards. So your second group is formed. Now we are left with 35 cards. So from the 35 cards, you are drawing 15 cards. Now we are left with 20 cards. And from that 20 cards, you are going to draw 20 cards. That's it. Is it clear? This directly I have used the C. That is the combination formula. So what we are getting here, 52 factorial divided by factorial 7 into 45 factorial into factorial 45 divided by 10 factorial into 35 factorial, 35 factorial, 15 factorial into 20 factorial, and 20C20 can be written as 20 factorial divided by 20 factorial into 1 factorial, right? Actually, it is coming to 1. Okay, so now if we cancel this, this will go off. Again, this will go off. So we are left with what? It is factorial 52 divided by 7 factorial, 10 factorial, 15 factorial and 20 factorial. Clear? Now you can easily see that this can be written directly from the question. How many cards are to be grouped? 52 cards. So in the numerator I have written 52 factorial, and you are dividing this 52 cards into 4 groups consisting of 7 cards, 10 cards, 15 cards and 20 cards. You see in the denominator I have simply divided by factorial 7, factorial 10, factorial 15 and factorial 20. That's it. So either you can start your problem in this way or you can write this thing directly. Okay, let me take another example. In how many different ways 9 balls can be grouped into groups of 2, 3 and 4 balls? So this can be arranged. You can do it by C. No problem, but what I'm trying to do, I'm trying to write this answer directly. So it will be what? Total number of balls to be distributed is 9. So it will be factorial 9 divided by, it has been divided into groups consisting of 2, 3 and 4 balls. So it will be divided by factorial 2, factorial 3 and factorial 4. That's it. Is it clear to all? So this is the total number of ways in which 9 balls can be grouped into groups of 2, 3 and 4 balls. So what we have learned so far, if we have been given objects, suppose, let me take for an example, 10 objects we have been given, and we have to divide this in, let us say, 2, 3 and 5 objects in 3 groups. That is, we are dividing this 10 objects into 3 groups, which will have, one group will have 2 objects, another group will have 3 objects, and another group will have 5 objects. So directly you can write the answer in this way: factorial 10 divided by factorial 2 into factorial 3 into factorial 5. That's it. And if you don't want to remember this, you can start with C. Here what you will do, you will write 10C2 because the first group will have 2 objects. So 10C2. Now we are left with 8. Out of that 8, you are going to choose 3. So that can be done in 8C 3 different ways. Now we are left with 5 objects. So 5 objects can be selected in 5C 5 different ways. So that way also you can start, or you can write the answer directly. Is it clear? So this is exactly how we distribute given objects into groups of unequal size. See, this is the term I have introduced. Unequal size. Why I'm saying that? Because have you observed one thing in our previous example also? See here, when I have used, there are 5 balls and we have grouped into 2 groups which are having 2 objects in one group and 3 objects in another group. Can you see that these 2 groups are of unequal size? What do you mean by unequal size? Unequal size means the number of objects which are present in the groups are all unequal. In the first group we are having, one group is having 2 objects and another group is having 3 objects. In the same way, if you see, all of these questions, they are all having, for the first one we are having 10 objects which has been distributed into 2 groups containing 4 and 6 objects. Can you see that your 2 groups are of unequal size? In this case also 7, 10, 15, 20, they are of unequal size. In this case also the group of 2, 3 and 4, they are of unequal size. Is this clear? So far whatever we have discussed, we have made some consideration, that is, number 1, all balls are distinct, and number 2, whatever groups formed, they are of unequal size. These 2 things we have considered while doing the problems that we have discussed so far. Now, let me just discuss about distribution of groups. As I told you in the beginning of our class that today we are going to discuss grouping of objects and distribution of groups simultaneously. So grouping of objects which are all distinct and of unequal size, that we have already discussed. And now we are going to discuss about distribution of these groups. Now in this example, we have seen that we have grouped 2 groups containing 2 objects and 3 objects. In how many different ways? In factorial 5 divided by factorial 2 into factorial 3. So that gives us 10 ways, right? So total there are 10 ways in which you can group, you can form 2 groups containing 2 and 3 objects. One group will have 2 objects, another group will have 3 objects. So there are 10 ways. Now the question is, if I want to distribute these 2 groups among 2 people, think in this way that we are having 2 distinct suites. Now I want to distribute these two sweets among two people. In how many different ways I can distribute it? So we are having two sweets that can be distributed in two different ways. Tell me yes or no. Because there are two people. In how many different ways you can distribute these two sweets to them? It's 2p2. Therefore, total number of ways in which this group so formed, consisting of two objects and three objects, can be distributed among two people in factorial two different ways. That is, 10 into 10 actually came from this calculation. So whatever answer we got after this calculation, in this case it is 10, you simply multiply this with 2p2, which is actually factorial 2. So that gives us 20 ways. Am I correct or not? So there are 20 ways of distributing these two groups among two people. That's it. Is it clear? Similarly, if we take the other example, see this one. Here, 10 objects being grouped into two groups, 4 and 6 objects. So that can be done. I mean, the group can be formed in this much total ways. Now, if I ask you that these two objects are to be distributed among two people, so in how many different ways you can distribute it? It will be simply 2p2, or you can write directly this thing as factorial 2. That's it. Is it clear or not? Similarly, in this case also, the total number of ways in which 52 cards are has been grouped into 4 groups consisting of 7, 10, 15 and 20 cards. Total number of ways is this. Now, in how many different ways this 4 group can be distributed among 4 people? So that can be done in factorial 52 divided by whatever answer we got. Since these groups are distributed among 4 people, so it will be 4p4, or you can write this thing as directly factorial 4. That's it. Now, if the same question if I give you, and after grouping into 4 groups, if I ask you in how many different ways these 4 groups can be given among 3 people, among 3 people, in how many different ways you can distribute these 4 groups among 3 people, then what you will do? You will simply say the total number of forming the group is this. And now these 4 groups are distributed among 3 people. So which can be done in 4p3 different ways. Tell me yes or no. Have you understood this? Even if I say that these 4 groups are to be distributed among 2 people, in how many different ways you can do? So whatever ways we got to form the group multiplied with 4p2. That's it. Because 4 groups, that has to be distributed among 2 people. So 2 people will get these 4 groups in how many ways? It is 4p2 different ways. So I have multiplied with that. Is it clear? Same thing here. If I say that these 3 groups formed by from these 9 balls, when divided into 3 groups containing 2, 3 and 4 balls, and if I say in how many different ways these 3 groups can be distributed among 3 people, it will be nothing but 3p3. And if I ask you that these 3 groups can be distributed among 2 people in how many different ways, simply replace this 3p3 by 3p2 different ways. That's it. Now, have you observed one thing? So far, whatever examples we have taken, we have seen that here there are 10 objects, and that 10 objects has been grouped into groups of 4 and 6 objects. That is, the total number of objects in 2 groups is 10. That is the total number of objects available or to given to us. Similarly, for this case, 7 plus 10 plus 15 plus 20. You are getting that thing as 52. So 52 has been distributed. I mean, it has been grouped into 4 groups containing 7, 10, 15, 20 cards. And if you add all the number of these cards in these 4 groups, you are going to get 52. Everywhere it is like that. You see, it is 2 plus 3 plus 4. That is 9. And 9 balls are available. Similarly, in the previous sum, there were 5 balls and you have grouped in 2 groups containing 2 and 3 balls. So 2 plus 3 again gives us 5. But what happened if I take an example like this? See this question. In how many different ways 20 balls can be grouped into 3 groups containing 2 balls, 4 balls and 6 balls? Now observe one thing, 2 plus 4 plus 6 is less than 20. Am I correct? So here the total number of balls are not being distributed. We are distributing into 3 groups. We are forming 3 groups which will contain the total number of balls which are less than the available number of balls. In that case, what will happen? Now, if I use directly the formula C, the combination formula, if we use it, how we will do that? The first group can be formed in 20C2 different ways. So now we are left with 18 balls. So that from 18 balls, we are going to select 4 balls to form the second group. And now 14 balls are available to us. From that 14 balls, you are drawing 6 balls to form the third group. So total number of ways of forming these 3 groups will be 20C2 into 18C4 into 14C6. So now if we simplify this, what we are going to have? Factorial 20 divided by factorial 2 factorial 18. Factorial 18 divided by factorial 4 into factorial 14. Factorial 14 divided by factorial 6 into factorial 8. Is it clear? So now if we cancel, what we are going to have? So we are actually getting factorial 20 divided by factorial 2, factorial 4, factorial 6. And now we are getting another term here, factorial 8. Now, why I have changed the color of factorial 8? Because what we have learned so far is that if suppose there are 10 balls and if you want to group in 3 groups which will contain say 2, 3 and 5 balls or 5 objects, you will directly write the answer in this way. Factorial 10 divided by factorial 2 into factorial 3 into factorial 5. In this case, you see, this part is exactly the same part. Because out of that 20 balls, you made 3 groups containing 2, 4 and 6 balls. So I have written factorial 20 divided by factorial 2 into factorial 4 into factorial 6. But my question is, why this factorial 8 is coming? Why this factorial 8 is coming? Now, it's a logic. And I will establish that logic. But before that, let me tell you, if I use the combination formula, we are getting this answer. So this is correct answer. But if I want to write it directly, then this one and the method that we have used in the previous sums are little different. There is a little difference between the previous form and this form. When there was 3 group, we used to divide by the number of objects of that group in this case. In that case. But in this case, an extra factorial is coming. And why it is so? The logic is, when we are having, say for an example, that on a table, you are having 20 marbles. And from that marble, I asked you to form 3 groups of 2 marbles, 4 marbles and 6 marbles. So the moment you go for 2 marbles, separation of 2 marbles, then 4 marbles, then 6 marbles, think about it. There will be one group. Automatically it will be formed which will have 8 remaining marbles. This particular group we have not considered. Unknowingly, this group is formed. And that is the reason why this factorial 8 came in our answer. Because there will be 8 marbles in that unknown group. That is why it has been, it has been written like factorial 8. This way you can think about it. Is this clear or not? Now, suppose if I say this group, now I want to distribute these 3 groups among 3 people. So what you will write? You will simply write this will be into factorial 3. Because actually 3 groups are formed and these 3 groups are now distributed among 3 people. So that can be done in 3p, 3 different ways. So it is multiplied with factorial 3. Is this clear or not? Let us say there are 10 balls. And now we have to make 3 groups containing 1 ball, 2 balls and 3 balls. Now if we use the formula C, in this case what we will write? I will write 10C1 into, this is the first group formed by choosing 1 ball from these 10 distinct balls. Now we are left with 9 balls. Out of that we are choosing 2 balls to form the second group. And now we are left with 7 balls, out of which we are choosing 3 balls to form the third group. So total number of ways of forming this group will be factorial 10 divided by factorial 1, factorial 9, factorial 9 over factorial 2 into factorial 7, factorial 7 divided by factorial 3 into factorial 4. Now if we cancel, we are going to have 7 goes off. See the answer what we are getting? It is factorial 10, factorial 1, factorial 2, factorial 3 and again this factorial 4 is coming. Is it clear? Why? Because this 4 will form an unknown group which will have 4 balls. Is it clear? So now if we want to write this answer directly, simply by using logic, what we will do? We will simply use the same thing. 10 balls are available, so factorial 10 in the numerator divided by the first group consists of 1 ball, factorial 1. The second group consists of 2 balls, factorial 2. The third group consists of 3 balls, factorial 3. And unknowingly, the rest balls, that is 4 balls, will form a group. So in that case also we have to divide it by factorial 4. So be very careful while you are writing this answer. If you do it by C, there is no harm, nothing to be remembered. But the moment you are using this formula directly by using the factorial notation, be very careful. Even in this case they have asked for forming 3 groups, but in this case unknowingly a group of 4 balls are formed. So that has to be divided by factorial 4. Remember in that way. Again I'm mentioning, if you are doing it by C, no need to remember anything. But if you are writing this answer directly, which is actually, expected when you solve problems in JEE, because where time is a major constant. So in that case, be careful. An unknown group of 4 balls is formed. So that has to be divided by factorial 4. Is it clear to all? Okay, so let me just summarize what we have done. Suppose if there are M, N and P balls. If there are M, N and P balls available, or M plus N plus P objects are available, out of which I have to form a group of M objects, N objects and P objects. So the total number of ways of forming those groups will be, directly if I write the answer, it will be M plus N plus P factorial divided by factorial M, factorial N and factorial P. That's it. Now, if I consider that we are having M, N and P, total objects available, but we have to form groups of M and N. I mean, two groups we have to form consisting of the objects M and N respectively. So what we will done? In how many different ways we will do? We will do in the same way, M plus N plus P factorial. I'm writing the answer directly. Look at carefully how I'm writing. So it will be factorial M into factorial M. But you cannot stop here. Unknowingly a group is formed which will consist of M plus N plus P minus M minus N. That is, there will be P objects in that unknown group. So that also has to be divided. Is it clear? Have you understood this problem clearly? So whenever they are saying that whatever objects is available, you have been said to form the group which will have the objects, and if you sum it up, you are going to have the same objects which is given to us. That is, whatever objects is available to us, you are forming the group by taking all those objects in different groups. This is one case when we directly write the formula that we have learned. But in case of the number of groups that is formed and the total number of elements or objects that are coming in that group, if you add it, it is less than the available number of objects. In that case, unknowingly a group is formed. So total number of elements in that unknown group has to be divided by its factorial. Is it clear now? Absolutely. And now if I ask you to distribute these three objects into say 3 people, so you will simply multiply this with 3p3 or factorial 3. Or if I say that distribute these 3 groups among 2 people, so in place of this 3p3, you have to write 3p2. Because 3 groups are available to you, that has to be distributed among 2 people. So which can be done in 3p2 different ways. Same thing here, we are having 2 groups. Actually, we are having 2 groups. Unknown group, I am not taking into my consideration. We are having 2 groups here. In our hand, we are having 2 groups. Now, if I ask you that please distribute these 2 groups among 2 people. So what you will do, you will simply do 2p2, or you can write this thing as factorial 2. That's it. Is it clear to everyone? Absolutely. Okay. So far, whatever we have done, we have seen that in all the illustrations, we have seen that the group size was unequal. In everywhere, the group size were unequal. Now, in this case, we will consider if the group size becomes same, then what happens? Let us check it. Suppose we are having 4 objects, A, B, C, D. Now, if I ask you to form 2 groups of 2 objects each, in how many different ways we can form this group? Now, according to our previous knowledge, if I go for that way, the answer should be 4c2 into 2c2. That should be the answer. It means it is same as if we directly write in the factorial notation, which you are actually getting the same thing from here, will be factorial 4 divided by factorial 2 into factorial 2. So that gives us how much? 24 divided by is 6 ways. So there are 6 ways of forming these 2 groups which will have 2 objects each. Let me just write all those groups possible. Let us say in one group we are having AB, the another group obviously we will have C and D, or AC, BD, AD, BC, or it can be BC, AD, or it can be BD, AC, or it can be CD, AB. So see, we actually got 6 such ways of forming this 2 group. Now you can ask me, sir, then where we are wrong? We are correct. I will say, please see these groups minutely. You will find that there are some repetitions which is already involved in this number of ways. You have formed 2 groups A, B, C, D. You see, we have also formed another group which is C, D, A, B. But does it have any significance to us? Suppose there are 4 marbles lying on the table. I told you to form 2 groups which will have 2 marbles each. So you have got AB in one group and CD in another group. Now these groups are not named, they are unnamed. So forming these 2 groups, AB, CD, in one group we are having AB marble, in another group we are having CD marble. Now if I say, no, first I have chosen CD, then AB. Does it have any significance? It represents exactly the same 2 groups. Yes or no? So that is why this ABCD division is same as your CDAB division. Okay? Because again I am telling you, I have simply asked you to form 2 groups. That's it. 2 groups. And I have not given any name. Because if I give name of the group, then it will become distinct. If I say that this group is, let us say 1 and this group is 2, then this selection, this group which contains AB and CD, this 2 will be different from CD and AB. Am I correct or not? Because now this CD has been identified by group 1 and this is identified by group 2. And in the first case, AB is identified by group 1 and CD is identified by group 2. So these 2 will be different. But here I have not said that these 2 groups are named. They are unnamed. And if they are unnamed group, then ABCD is same as CDAB because this group has no name. So they are identical to me. Are you getting my point? Therefore, ABCD, when the group is unnamed, in that case, your ABCD and CDAB, these are the identical one. Now we can easily see that ACBD, again this repetition is coming, BDAC. AD is here, ADBC, again the same repetition is occurring, BCAD. That is, these 3 cases are exactly same as these 3 cases. When the groups, again I am mentioning, when the groups are not named, they are unnamed groups. So this is actually the line of symmetry. It is dividing this total 6 arrangement or the 6 ways of dividing these 4 objects into 2 groups containing 2 objects each into 2 equal halves. Therefore, the actual number of ways of forming these 2 groups containing 2 objects each will be not 6 ways. It will be 6 divided by factorial 2, that is 3 ways. Is it clear or not? Have you understood this or not? Because the line of symmetry actually dividing this thing, the total ways of forming the groups into 2 equal halves. So therefore, I have divided by factorial 2 to get the total number of distinct ways of forming two groups having two objects each. Is this clear? Now the question can come, sir, suppose if there would have been three groups, suppose we are having 6 objects here, and I ask you to form a group of 3 groups which will contain 2 objects each. So in that case, will I divide by factorial 2? No. In that case, you have to divide it by factorial 3. So always remember that whenever groups are of equal size, when, let us say, when R groups are of equal size, okay, then whatever answer we are getting, what answer we got? We actually got this answer. It was what? Factorial 4 divided by factorial 2, factorial 2. See, the same thing I have already applied when the group size was unequal. So total 4 objects were there. So I will write that thing as factorial 4 divided by factorial 2 into factorial 2. But the only difference is that when the group size are equal, then we simply divide it by the number of equal groups. In this case, if I say that there are R groups of equal size, whatever answer we are getting, as we have done in the previous way, in this also we will do the same thing, but it will be divided by factorial R. Remember in that way. If I say, suppose there are 6 objects and we have to form 3 groups, each containing 2 objects. So in that case, what will be the answer? It will be actually factorial 6 divided by factorial 2 into factorial 2 into factorial 2. Till this part, it is exactly the same when the group size were not equal. They were different. But in this case, since the 3 groups are of equal size, so all I will do is I will divide the thing by factorial 3. That's it. If there are R groups of equal size, then we will divide it by factorial R. That's it. Is this conception clear or not? Let me take some illustrations to understand this conception more clearly. See this question. In how many different ways can a pack of 52 cards can be distributed equally among 4 people? Okay, distribution I will come later on. First, these 52 cards are to be divided into 4 equal parts. That is, we have to form 4 groups which will contain equal number of cards. So each group will have 13 cards each. 4 groups will have 13 cards each. So if I go, so what will be the total number of ways of forming this group? It will be factorial 52 divided by factorial 13 into factorial 13 into factorial 13 into factorial 13. This is same as when the group size was not equal, as I told you right now. Now, these 4 groups are of equal size. Therefore, the total number of ways of forming these equal 4 groups will be divided by factorial 4. That's it. Is this clear to you? 52 cards I have to divide it into 4 groups of 13 cards each. That is, they are equally grouped. So that can be done in factorial 52 divided by factorial 13 4 times into, since the 4 groups are of equal size, I have divided by factorial 4. That's it. So this is the total number of ways in which the 4 groups can be formed. Now the question is, these 4 groups are to be distributed among 4 people. So in how many different ways you can do that? Total number of ways of forming 4 groups of equal size. Now this group has to be distributed among 4 people. So it will be 4p4, or you can say it is factorial 4. So the total number of ways of distributing these 4 equal groups among 4 people in factorial 52 divided by factorial 13 whole 4. Because from here you are going to have factorial 4, this and this will go off. Is this clear? Is this conception clear? Let me take another example. See this question. In how many different ways can a pack of 52 cards be divided into 4 sets of 10, 14, 14 and 14 cards each? So what you are doing, 52 cards are there. You are dividing it in 4 groups containing 10 cards, 14 cards, 14 cards and 14 cards, right? So what will be the total number of ways of grouping those cards? It will be factorial 52 divided by factorial 10 into factorial 14 3 times. So it will be factorial 14 whole cube. But here these 3 groups are of equal size. They are of equal size. Now as they are of equal size, so I have to divide it by factorial 3. That's it. So this is the total number of ways of dividing or grouping 4 groups containing 10, 14, 14 and 14 cards. Okay. Now what is the second type? The second question. In how many different ways it will be distributed among 4 players? So you are having 4 groups and you are distributing among 4 players. So that can be done in 4p4 different ways. So your final answer for distributing these 4 groups among 4 players will be factorial 14 whole cube into factorial 3, because just one second, factorial 4 whole cube into factorial 4, right? Because the 4p4 is basically factorial 4 and that will be your answer. Is it clear to everyone? Okay, let me take another problem. See this question. This question already I have done in my previous class where I have done inclusion-exclusion principle, and there I told you that when we will do grouping, then we will solve exactly the same sum. Now I'm going to solve that same sum here. The question is, there are 5 distinct balls. There are 5 distinct balls. Let me just give a name of this ball since they are distinct. And we are having 3 boxes. Okay, let us say this is box 1, this is box 2, and this is box 3. Right? Now the question is, in how many different ways these 5 balls can be distributed among these 3 boxes such that no box remains empty. No box remains empty. Now, first of all, I'm doing this problem in a wrong way. And I will tell you why it is wrong. First, you people try to understand why this method that I am opting now is wrong. 5 distinct balls are there to be distributed in these 3 boxes such that no box remains empty. So let me do one thing. Let me first do one thing. Let us fill 1 balls. Let us fill 1 ball each in the first box, in the second box, and in the third box. So the first box can be filled In how many different ways? It can be filled in 5 different ways. Any of these 5 balls can go in box 1. The remaining 4 balls, 1 ball will go in box 2. That can be done in 4 different ways. And from the remaining 3 balls, 1 ball will go in box 3, which can be done in 3 different ways. So this is the total number of ways in which 1 ball has been placed in box 1, box 2 and box 3. Is it clear? Now, we are left with, since 3 balls are already taken their places in the boxes, so we are left with 2 balls. Now, these 2 balls can be placed anywhere in this box, because already your box is filled with 1 ball. So whether the other ball comes or not, it doesn't matter, because in our condition the question was no box remains empty and we have fulfilled that condition. Now whether the other 2 balls comes or not, it doesn't matter to me. So in how many different ways the remaining 2 balls can go in these 3 boxes? Okay, so let us say we are left with these 2 balls D and D. Let us say for an example. Now the ball D can go in any of the 3 ways. It can be placed in any of the 3 boxes. So that can be done in 3 different ways. So ball D can be placed in any of these 3 boxes in 3 different ways. Again, ball E, which is the last ball we are having, that can also be placed in these 3 boxes in 3 different ways, because it can go to any of these 3 boxes. So that can also be done in 3 different ways. So in this case, our answer should be 20 into 27. That gives us 540. Am I correct? So your answer should be 540. Okay, in this case. But this is absolutely wrong. This is absolutely wrong. Can you tell me why it is so? Why this method is wrong? What wrong I have done? We have 5 balls and we have 3 boxes. No boxes should remain empty. You have to place all these 5 balls in these 3 boxes. Okay. So what I have done first is I have kept 1 ball each in 3 boxes. And then we are left with 2 balls. I have placed these 2 balls in any of these 3 boxes. So all these 5 balls are placed in 3 boxes and no box remains empty. So if this is the question, then my method is absolutely correct. Why it is wrong? Why I am saying it is wrong? You see it very carefully. There are some repetitions which we have not considered. In this calculation, a lot of repetitions came. I'm telling you why. Let me just denote this is box 1, box 2, box 3. Now let us say for an example, box A, when we are placing 1 ball each in these boxes, let us say A came in box 1, B came in box 2 and C came in box 3. And now we are left with 2 balls D and E. Now this D and D can be placed in any of these 3 boxes. Let me take one of that way B. D is placed in box 1 and E is placed in box 2. So this is one arrangement which has already been considered in this 540. Okay. Now see another case. Suppose in the first hand, we are placing 1 ball each in 3 boxes. Let us say D came in box 1, E came in box 2 and C came in box 3. So we are left with 2 balls A and B. And now we have to place these 2 balls in these 3 boxes. Let us say we have placed A in box 1 and B in box 2. Now please see this thing very carefully. Box 1 contains the ball D and A. Box 2 contains the ball EB. and box 3 contains the ball C, which is also one option that has considered here in this calculation. But can you observe one thing? This arrangement, this distribution and this distribution, they are exactly same. Are you getting the point? They are exactly same. And we have considered these two, this and this, as two different ways. And that is why this number is coming so big. Are you getting my point? So for all those arrangements, there will be lot of repetitions, which we have already considered. So we cannot do it by this method. You should know the wrong approach. Because whenever you are doing this kind of problem, sometimes this thing will come in your mind. Why I cannot apply this method? So that is why I have explained why you cannot use this method. Okay, so now let us come to the right approach. So for the right approach, what I will do, I will first make a group. I will first make a group of these 5 balls. In this, we are forming 3 groups. And all these groups will be filled by these 5 balls. So what can be the group size? It can be 1, 1, 3. Because no box can remain empty. At least one ball has to be given in every box. Or it can be 2, 2, 1. That's it. No other group can be formed where no groups remains empty. Is it clear? So now the question is, in how many different ways you can form this group 1, 1, 3. It will be nothing but factorial 5 divided by factorial 1 whole square factorial 3. Now we are having 2 groups of equal size, so it has to be divided by factorial 2. Is it clear? Now this is the total number of ways of forming the group in which group contains 1 ball and 3 balls. Now this number of ways of forming this group will be distributed in 3 distinct boxes. So that can be done in factorial 3 different ways. Right? Okay. So now let us consider the second case, or this is the second case. 2, 2, 1. The group should be formed like one group will contain 2 balls, another group will contain 2 balls, and the third group will contain 1 ball. So that can be done in factorial 5 divided by factorial 2 whole square into factorial 1. But these 2 groups are of equal size, so it has to be divided by factorial 2. Now this number of ways of forming the group are to be now distributed in the 3 distinct boxes. So that can be done in factorial 3 different ways. So the total number of ways will be either this or this. So what will be this? Let me just calculate this one. So it's 120 divided by 2 gives us 60. This is 120 into 6 divided by factorial 2 is 2. So 2 squared, that gives us 4, and here it is 2. So 4, this gives us 32, this is 3, so it is coming to 90. Therefore, the total number of ways in which these 5 distinct balls can be distributed in 3 different boxes such that no box remains empty is 60 plus 90, that is 150. And that's your answer. Is it clear? We have actually done this sum in inclusion-exclusion lecture also, right? So this sum actually came in JEE Advanced, IIT Advanced 2012. So it's a very, very important sum. So have you understood this? Now, first thing that I will tell you, have you understood the wrong approach? Very important to understand that. And then you do the right thing. Right thing is what? I have simply distributed these 5 balls First in 3 groups. These 3 groups will contain 5 balls. In what are the ways that you can do? It can be either 1, 1, 3. Distribution can be 1, 1, 3. In the group. Or the balls can be, in group in the way 2, 2, 1. So these 2 types of groups we will form, and then we will simply distribute it in 3 different boxes. Is it clear? Okay, let's move for the next problem. Now in this question they have said that n different toys are to be distributed among n children. Find the total number of ways in which these toys can be distributed so that exactly one child gets no toy. So there is an hidden condition already given. That is, out of this n child, there is exactly one child who is not going to get any toy. So the other n-1 children will get at least one toy. Because if any one of the child among that n-1 children, if he gets no toy, it means what? There will be 2 children who are not getting any toy. But that is not the question. The question is exactly one child will get no toy. So let us just first find out which child is going to get no toy. Out of that n children, one child can be selected in NC1 different ways, and this child is not going to get any toy. So now we are left with n-1 children. And this n-1 children will get these n toys in such a way that each and every child must get at least one toy. Okay, so what I'm trying to do here is, first of all, let us make groups of, group of n-1 groups such that the group will contain, each group will contain at least one toy. So if you want to distribute this n toys into n-1 groups where each group will have at least one toy, so the division in the groups can be in this way: 1, 1, 1, all 1, and one group will contain 2 toys. So here the total number of groups are n-1, and n-2 groups will have one toy. So n-2 groups each are having one toy, and one group will have 2 toys. So in how many different ways you can form this group? Total number of toys is n, so it will be factorial n divided by factorial 1. These n-2 groups are of equal size. So it will be n-1 to the power, factorial 1 to the power n-2 into, since these n-2 groups are identical, so it will be n-2 factorial, and one group is having 2 toys, so it has to be divided by, again, factorial 2. Is it clear? So this is coming like factorial n divided by n-2 factorial into factorial 2, right? So now this is the total number of ways in which n toys are divided into n-1 groups. Now these groups are to be distributed among n-1 children. So that can be done, this distribution can be done in factorial n-1. Is it clear? Now, one child is getting no toy. Now, which child In how many different ways you can select that child? It is NC1. Therefore, total number of ways in which this n different toys can be distributed among n children such that exactly one child is not getting any toy will be this. Are you getting the point? Why this NC1 came? Because I have to first select which child is not getting any toy. So that can be selected in NC1 different ways. And now these n-1 groups are formed in this number of total ways. And now we are distributing these groups into n-1 child. So that can be done in n-1 factorial. Therefore, the final answer for this will be NC1 is actually n-1 factorial is there. And this is basically nothing but NC2. Okay? And n into n-1 factorial gives us factorial n into NC2. Is it clear to all of you? Have you understood this problem? They have said that exactly one child out of these n children is not going to get any toy. So first I have selected which child is not getting any toy. That can be done in NC1 different ways. Now we are left with n-1 children. Now out of these n-1 children, no child will get, every child will get at least one toy. Otherwise, the condition in the given question will be violated. Because out of this n-1 child, if one child doesn't get any toy, it means what? That there will be two children in that group where they are not receiving any toys. But that is not the question. The question is exactly one child will not get any toy. Is it clear? So now we have distributed n toys in n-1 groups, in which every group will have at least one toy, and that can be done in factorial n divided by n-2 factorial into factorial 2. Now why I have divided by factorial n-2? It's because there are n-2 groups in which each group contains one toy. So that is why these n-2 groups are identical, and that's the reason why I have divided by n-2 factorial into factorial 2, because one group, it has two toys. Okay? And then you have distributed this group among n-1 children. So I have multiplied it with n-1 factorial. That's it. Have you understood this problem? Okay, so let's move for answer is factorial n into NC2. That's exactly what we got. Now let's move for the next conception. So far we have learned grouping of distinct objects of unequal and equal group size, as well as we have learned how to distribute these groups. In this section we are going to discuss about grouping of identical objects and then distributing it to some heads. Okay? Now see, suppose if I give you that we are having 5 distinct balls. Let us say they are A, B, C, D and E. Okay? Now I want to form a group having 1, 2 and 2 balls. So this grouping can be done in how many different ways? Factorial 5 divided by factorial 2 whole square into factorial 2. I hope you have understood why I have divided by factorial 2, because these two groups are of equal size. Hence it gives us 120 divided by 8, that gives us 15. So there are 15 ways in which these 5 distinct balls can be grouped into 3 groups, which will contain one object or one ball, 2 balls and 2 balls. So the total number of distinct ways of distributing it in groups are these ways. These are the 15 ways which we got. Now let us take one such group from these 15 groups that we have already formed. Let me take the first one. One group contains A, another group contains the object BC, and the third group contains, I should not say third group because the moment I say third group, it becomes identified. Groups are not identified. So the three groups which contain the balls A, one group contains balls B and C, another group contains ball D and E. Now I want to distribute this. There are 15 ways of forming groups containing 1, 2 and 2 balls. Now if I want to distribute these groups among 3 people, the total number of ways will be what? 15 into factorial 3. That gives us 15 into 6. That is, there are 90 ways of distributing these 3 groups among 3 people. Let us say the 3 people be X, Y and Z. And let me consider only the first group. I mean the first distribution of the group we are considering. That one group is having A ball, another group is having B and C balls, and the other group is having D and E balls. Now if I want to distribute these 3 groups among 3 people X, Y, Z, that can be done, you see, in these 6 ways. Am I correct? So that is why for every group, for this arrangement, you can distribute it among 3 people in 6 ways. Again, for this arrangement, I mean for this ways of forming the group, this group can be again distributed among 3 people X, Y, Z in 6 ways and so on. So there are 15 such groups formed, and that when distributed among 3 people X, Y, Z, for each it can be distributed in 6 ways. So there will be total 15 into 6, that is 90 ways. This is the case when all balls are distinct. Now, suppose if we take 5 balls which are exactly same, that is they are identical, you cannot distinguish one from the other. Now if I ask you to form a group from 3 groups which will have 1 ball, 2 balls and 2 balls. So in how many different ways you can form this group? Can you tell me? There is only one way, there is only one possibility, that one group will have 1 ball, another group will have 2 balls, and the rest group will have the 2 rest balls. That's it. This is the only way, only one way we are having to group it into 3 groups containing 1, 2 and 2 balls. This is when these 3 balls are identical. Are you getting the point or not? Because you see, in the distinct case, A, B, C, B, D, it is one way of grouping. Then again, A, B, D, C, E, this is another way of grouping. But if you exchange these 2 balls here, it is not going to change the meaning of the question. It remains same. That is why there is only one way of dividing into 3 groups containing 1, 2 and 2 balls. Now my question is, if I want to distribute this group among 3 people X, Y, Z, in how many different ways we can do that? Obviously, we are having 3 groups, one containing 1 ball, another group containing 2 balls, and the third group containing 2 balls. Now, all balls are identical. So in how many different ways these three groups can be distributed among these three people? It will be factorial 3 divided by factorial 2y, because two groups are these two groups are identical. Because they are having the same number of balls. You cannot distinguish these two balls from this group and two balls from this group. You cannot distinguish. They are identical. Therefore, we have divided by factorial 2. That is, it gives us, there are three ways. There are three ways. And what are the way? We can go by analyzing it mathematically. We can say that this person got one ball. Then other one is, this is 2. Let me just write it here. X got 1, Y got 2, Z got 2. Or X got 2, Y got 1, Z got 2. Or X got 2 balls, Y got 2 balls, and Z got 1 ball. That's it. That is why we got, there are three ways. Is it clear to all of you? Is this much clear to all of you? Absolutely. Okay. Now, can we observe a major difference when the balls were distinct and when balls are identical in case of distributing those balls to some heads? Have you observed the major difference? The major difference is that when the balls are all distinct, in that case, we are concerned about which ball is going to whom. Yes or no? Which ball is going to whom, that we are concerning in case of distinct balls. But in case of identical balls, we are not concerned about which ball is going to whom. Here we are concerned about how many number of balls are going to whom. You see, when in this distribution, X got 1 ball, Y got 2 balls, and Z got 2 balls. Now, when A gets 2 balls, B gets 1 ball, and Z gets 2 balls, it is a different distribution. It is another way of distributing these three groups among X, Y, and Z. Why? Because the number of balls has been changed. But in this case, you see, for the distinct objects, this one, X is getting, let us consider this one. X is getting A, Y is getting BC, and Z is getting DE. But in the second case, which is another way of distributing this group, when X is getting A, Y is getting DE, and Z is getting BC. Both are getting 2 balls each, Y and Z. But here, which ball is going, it is actually a matter to be concerned. Yes or no? That is why these two are different ways of distributing these two groups among these three persons X, Y, and Z. But in case of identical objects, that we are not concerned about. We are only concerned about how many number of balls are going to whom. That's it. Is it clear to all of you? Have you understood this much clearly? Okay. So, can we say, let me just go in the next page. Can we say, suppose we are having 5 identical balls, and if I ask you, in how many different ways you can distribute these 5 balls among 3 people. Listen it very carefully. It's a very, very important theory I'm going to discuss in permutation combination. There are 5 identical balls. These are 5 identical balls. Okay? Now, I want to distribute these 5 identical balls among these 3 persons, let us say X, Y, and Z. Now, if I say that there is no restriction, there is no restrictions. What do you mean by that? It means that any one of these X, Y, and Z can receive any amount of balls. That is, the first person, maybe X, maybe Y, maybe Z, will receive no balls. That is also possible. So in this case, we can simply bypass grouping of balls. Because I know that for grouping, any grouping for identical balls, whether it is of equal size or not, it is going to be done only in one way. So if I want to distribute these 5 identical balls among these 3 people X, Y, Z, where we are only concerned about which person is getting how many number of balls, is it not the same way of saying that in how many different ways this 3 person X, Y, Z will receive 5 balls when there is no restriction? It is same as distributing these 5 identical balls among the 3 person X, Y, Z when there is no restriction. Is this clear to everyone? So now to solve this problem, we are going to adopt a wonderful method which is also called Beggar's method, or it is called partition method, or it is called ball and stick method. But whatever may be the name of this method, the method used is really a unique method to solve this kind of problems. But remember, to use this method, you have 2 restrictions. Number 1, your balls or the objects, they are to be identical. This is the first condition. And the number 2, the second condition is that there is no restriction. Very, very important. There is no restrictions. Now the question can come, sir, if there is any restriction, can we use this method? Answer is no. If there is any restriction, if I say that that person will get at least 2 balls or 3 balls or at least 1 ball, everyone must get at least 1 ball. This kind of restrictions, whenever I impose, you cannot use this method directly. Then what to do? There are 2 ways of doing this. One is you have to convert the thing in such a way that the problem becomes similar to the conditions given to us. That is, balls are identical, that is already given, but there will not be any restrictions. We will manipulate the problem in such a way that there will be no restrictions. If that thing is there, then we can use this method that we are going to use here, right? We will take examples and we will understand it better way. Now, there is another way also. If you don't want to go by that way, then you have to go in forming the groups, and then you have to distribute that groups among the people. Right? So there are 2 ways. So don't try to, remember this thing right now, because the moment we are going to take the illustrations, you will understand it in a better way. Right? Okay. So now the question is, In how many different ways? Actually, our problem comes to this point that in how many different ways these 5 identical balls can be distributed among these 3 persons, X, Y, and Z. So to do this, the partition method or Beggar method, whichever way you call it, it says that you do one thing. These 5 balls are to be distributed among these 3 people. You introduce 2 separators. You introduce 2 separators. This is also called the partition. Because if I introduce 2 partitions here, observe carefully, it has been divided into 3 groups. One group is containing 2 balls, the second one is containing 2 balls, and the third one is containing 1 ball. So X is receiving, in this way we can think, X is receiving 2 balls, Y is receiving 2 balls, and Z is receiving 1 ball. So it is one way of distributing these 5 identical balls among these 3 people, X, Y, and Z. Now suppose if I remove this separator from here and if we place it, let us say, here, then what happens? You see, in the left side of this separator, there are no balls. It means that your X will receive 0 balls. Your Y will receive 4 balls. And your Z will receive 1 ball. This is also a way of distributing these 5 identical balls to these 3 people. If I remove this separator from here and if I place the separator here, what happens? Your X receives 0 balls, your Y receives 5 balls, and your Z receives again 0 ball. Again, this is another way of distributing these 5 balls among these 3 people, X, Y, and Z. At the same time, you can do one thing also. You can remove this separator from here and you can place it here. Then what happens? Simple. Here there are no balls, therefore X will receive 0 balls. There is again no balls between these 2 separators, therefore your Y is going to receive 0 balls. But your Z in that case will receive 5 balls. Is it clear? So, just now what we have said is that the total number of ways of arranging these 5 identical balls and these 2 separators is the total number of ways in which these 5 identical balls can be distributed among these 3 persons, X, Y, and Z. Yes or no? So in how many different ways that can be done? There are 5 balls and there are 2 separators. So they can arrange among themselves in factorial 5 plus 2, that is 7 factorial, divided by 5 balls are identical, so divided by factorial 5. 2 separators are identical, so it is divided by factorial 2. So that gives us what? Factorial 7 by factorial 5 into factorial 2. That's it. That is the total number of ways of distributing these 5 identical balls among X, Y, and Z. Have you understood this? Is it clear to all? Now, this can also be written as 7C2. Now, if you want to generate a formula, we can say in this way that here there is 7C2, right? Now, let me try to, manipulate this 7C2 in such a way that it involves this 5 as well as it involves this 3 person X, Y, and Z. So, can we write this 7C2 in this way? That 5 plus 3 minus 1, C3 minus 1. Sir, why you have written in this way? I have a reason for that. You see, 3 minus 1 means it is the total number of separators. Am I correct? This is the total number of separators. And whatever is here, the same thing is here, right? Try to remember in this way. And this one is the total number of identical objects given to us. Total number of identical objects given to us. Is it clear? So now, if we say that there are, let us say for an example, there are n identical balls. There are n identical balls. Now we are trying to generate a formula out of this. Now I want to distribute these n identical balls among R people. Among R people. So as R people are there, so we must introduce R minus 1 separators. Okay? Now we are actually having n identical balls and R minus 1 separator. So they can arrange among themselves in n plus R minus 1 factorial divided by, since n identical balls are identical, so it has to be divided by factorial n. And all these R minus 1 separators, they are also identical, so you have to divide it by factorial R minus 1, which can also be written as n plus R minus 1 C R minus 1. Okay? So this is the total number of ways of distributing n identical balls among R people. Is it clear to everyone or not? So this formula is a unique formula of solving this kind of problem. But there are two restrictions. One is, number one, all the object has to be identical. Otherwise you cannot use this formula. And number two, there should not be any restriction. No restriction. Any number of objects can go to anybody. It can be 0, it can be 1, it can be 2, anything. There is no restriction. If these two conditions are fulfilled, we can use this partition method or Beggar method or ball and stick method, whichever name you call it. Is it clear? So now we can take one very quick example. Let us say we are having 20 identical balls. And we have to distribute these 20 identical balls among 5 people. In how many different ways you can distribute these 20 identical balls among 5 people? So how to do that? Directly use the formula. I can use this Beggar's method because here there is no restriction and all the balls are identical. So these two conditions are fulfilling. So we can say the total number of ways of distributing these 20 identical balls among 5 people will be 20 plus 5 minus 1 C 5 minus 1. We are exactly using this formula, n plus R minus 1 C R minus 1. So your answer will be 24 C4. This is the total number of ways of distributing these 20 balls among 5 people. Is it clear to all of you? Absolutely. So let me take an example to illustrate this thing more clearly. See this problem. 4 boys are picking 15 mangoes. In how many ways can they divide them? So we are having, all mangoes are identical. So we are having 15 identical objects. And these 15 identical objects, in this case they are mangoes. These 15 identical mangoes are to be distributed among these 4 boys. So naturally there is no restriction. It may so happen that some boys are getting no mangoes. That is also possible. So there is no restriction in this case. And all the objects are identical. So can we use our partition or Beggar method? Yes, we can easily use that because it is fulfilling our two conditions. So now we are having 15 mangoes, and what was the formula for Beggar method? It is n plus R minus 1 C R minus 1, What is n? N in our case is 15. That is the number of identical objects given to us. R is the number of groups it has to be divided. In this case, we are having 4 boys. So we have to divide this in 4 groups. So R is 4 here. So if I use this formula directly, what we will get? We will say 15 plus 4 minus 1 C, 4 minus 1. So that gives us 18C3. Is it clear? So there are total 18C3 different ways in which this 15 mangoes, identical mangoes, can be distributed among these 4 people where there is no restriction. Anybody can get any number of mangoes, including 0. Is it clear to everyone? Have you understood the application of this Beggar's method? Okay, so let's move for the next problem. In this question, they have said that there are 5 identical balls that can be distributed into 3 different boxes so that no box remains empty. Now the problem started. What is the problem? I cannot use Beggar's method directly here. Why? Because here there is a restriction. What is that restriction? That each box must contain at least 1 ball. So I cannot use Beggar's method because Beggar's method, what was the condition for Beggar's method? All the objects should be identical, number 1, and number 2, there should not be any restriction. But here restriction is given. So I cannot use Beggar's method or partition method directly in this case. There are 2 ways of solving this sum. First, I will try to manipulate this problem in such a way that we will be able to use the partition method. First, you see that. This is my method 1. We are having 5 identical balls and we are having 3 different boxes. Now, since they have said that no box can remain empty, this is say box 1, box 2 and box 3. So what I am doing here, I am simply giving 1 ball each to these 3 boxes. Any 1 ball, because these 5 balls are identical. So 1 ball can be given in B1, 1 ball is given in B2, and 1 ball is given in B3. That can be done only in one way because the balls are identical. It doesn't matter which ball is coming to which box. So there is only one way in which these 3 balls are placed, 1 each in each box. So what does it make? It says, now we are left with, suppose these 3 balls are gone. So now we are left with these 2 balls. Now these 2 balls can be distributed in these 3 boxes without any restriction. Are you getting the point? 3 balls are already given, 1 each to every box. So now you are left with 2 balls. Now whether that ball is coming in 1 box or not, it doesn't matter to me because the condition given in the question is fulfilled. That at least 1 ball should be there in every box. That I have already done in the beginning of the sum. So now whether these 2 balls, whether it comes in box 1 or box 2 or box 8, it doesn't matter to me. Because 1 ball is already present in that box implies that no box remains empty. So now when we are left with these 2 balls, we can distribute these 2 balls in 3 boxes. In how many different ways? Same question. We are having 2 identical objects and it has to be distributed among 3 people. Let us say X, Y and Z. So total number of ways will be what? It will be 2. What was the formula? N plus R minus 1 C R minus 1. Here n is 2, R is how much? R is what? Total number of variables. The variable are, or the total number of heads, you can say in this case. It is X, Y, Z. So plus 3 minus 1, C 3 minus 1. So that gives us how much? 4C2. That gives us 6 ways. So there are 6 ways in which these 5 balls can be distributed in these 3 boxes such that no box remains empty. Have you understood this method? In this method, in the problem, in the first time when we see the problem, we cannot use the Beggar's method directly. The problem is that here the restriction is there. Because I told you, Beggar's method or partition method can only be applied when there is no restriction. But here there is restriction. So what I have done in my first method is that I have removed that restriction. How? I simply put 1 ball each in every box. Now we are left with 2 balls and now we are free to distribute these 2 balls in 3 boxes in any way you want. That is, there is no restriction. So for these 2 balls, when you are distributing among in the 3 boxes, there is no restriction. So I can use the Beggar's method, and exactly that I have done to get my answer as 6 ways. Is it clear? Okay, so let me just try to do it by another method. We have been given 5 identical balls and it has to be distributed into 3 different boxes so that no box remains empty. Let me first make a group of 1, 1, 3 or 1, 2, 2. We are making 3 groups containing 1 element, 1 ball and 3 balls, and or we are making another group of 3 groups which will have 1 ball, 2 balls and 2 balls. Now, the question is 1, 1, 3. This division of the group can be done in only one way, as I told you, because their balls are identical. Now, in how many different ways these 3 groups can be distributed among 3 different boxes? That can be done in factorial 3 divided by factorial 2 ways. Tell me yes or no. Why I have divided by factorial 2? Because you see, we are having 3 groups in which we are having 1 ball and 3 balls. Now, these 2 groups are identical. These 2 groups are identical. So when you are distributing these 3 groups among 3 boxes, in that case, these 2 groups will act as an identical object. And that is the reason why I have divided by factorial 2 ways. So in this case, the total number of ways will be 6 divided by 2. That gives us 3 ways. Am I correct? Same thing for the second one. Here the group is like this. One group is having 1 ball. The other group is having 2 balls. And the third group is having 2 balls. Now these 3 groups, when distributed among 3 boxes, that can be done in factorial 3 divided by factorial 2 ways. Again, why is I have divided by factorial 2? Because here these 2 groups are identical. So this gives us what? It gives us 3 ways again. So total number of ways is either this or this. So that gives us total 6 ways. Is it clear or not? Is this clear or not? Have you understood? So first what I have done, first I have manipulated the problem in such a way so that we can use Beggar method. You can adopt this method, or you can simply go for going into division into groups and then you are distributing that groups to that boxes. That way also you can proceed. That is why I've shown you 2 methods, right? Let us take another example. See this question. Find the number of ways of distributing 8 alike pens 6 alike pencils and 4 alike books among 3 students. Among 3 students, right? Each such that every student gets at least 1 pencil. Now, again, this is creating a problem. At least 1 pencil. Objects of same kind are alike. In this case, we would have used Beggar's method directly in the first hand. But since a restriction is given for the pencil, I cannot use that Beggar's method directly here. So what to do? Let us see. There are 3 people. And now we are having 8 alike pens. We are having 6 alike pencils. And we are having 4 alike books. Look at carefully. Okay. Now, for these 8 pens, number 1, they are identical. Number 2, there is no restriction. Because any number of pens can go to any number of these 3 students. So there is no restrictions in distributing these 8 identical pens among these 3 students. So in this case, particularly in the case of pens, I can use my Beggar's method. It will be what? There are 8 pens. So here N is 8. And here R is, there are 3 students. So R is 3. So total number of ways of distributing these 8 pens among these 3 students will be 8 plus 3 minus 1, C3 minus 1. So that gives us 10 C2 ways. So there are 10 C2 ways in which these 8 identical pens can be distributed among these 3 students. Okay, but there is a problem in case of pencils. In case of pencils, we cannot use the Beggar's method directly because in the question they have given every student gets at least 1 pencil. So in the first time what I'm trying to do, I'm simply giving 1 pencil each to these 3 students. So these 3 pencils are gone. These 3 pencils I have given 1 pencil each to every student. Since the pencils are identical, it doesn't matter which pencil is going to which student. Now we are left with 3 pencils. And these 3 pencils, when distributed among these 3 students without any restriction, then the condition given in the question is fulfilled. Because you see, in these 3 pencils, if I divide it among these 3 students without any restriction, so what, the worst case, what can happen is that all these 3 pencils are going to 1 person. It's okay. All these 3 pencils went to 1 student. It's okay because it is fulfilling our condition which is given in the question that every student should get at least 1 pencil because they are having 1 pencil each. So we are free to distribute these 3 pencils among these 3 students. Okay? So in how many different ways we can do? Here your N is 3 because 3 pencils are there. And your R, that is the number of heads to be distributed, is again 3. So the total number of ways of distributing these 3 pencils among these 3 students where there is no restriction is 3 plus 3 minus 1, C3 minus 1. That gives us 5 C2 different ways. Am I correct or not? Right? Now, in case of books, again, there is no restriction. 4 identical books are to be distributed among these 3 people. 3 students. So we are free to do anything because there is no restriction. So total number of ways will be 4 plus 3 minus 1 C, 3 minus 1. That gives us 6 C2 ways. Am I correct? So 10 C2 is the total number of ways of distributing the pens. 5 C2 is the total number of ways of distributing the pencils so that each one gets at least 1 pencil. And 6 C2 are the total number of ways of distributing these 4 identical books to these 3 students. So total number of ways in which these objects can be distributed to these 3 students is 10C2 into 5C2 into 6C2. Again, I'm not going for any calculation. Calculation you can do by yourself. But have you understood the logic? Have you understood the logic? That is the main part of this. You know, my main motto is to make you understand the logic behind it. How we are applying Beggar's method. Again, I'm telling you, partition method is a unique method of solving this kind of sums. But only, you know, the drawback that we have, I should not say drawback, but it's okay. We have only 2 restrictions. One is objects has to be identical. And number 2, there should not be any restriction. So even if restriction is there in the problem, as I've shown you in 2 sums, you have to manipulate the problem in such a way that this restriction part is over, right? So we have no restrictions, we are free to distribute the objects, and we will use the partition method to get its answer. Is it clear to everyone? Absolutely? Okay. So let's extend our discussion, whatever we have learned right now, in finding out the number of integral solutions of equation. Let us try to understand it with the help of an example. Say this question. Find the number of non-negative integral solutions of this equation. The equation given to us is x plus y plus z equals to 8. There are 3 variables, x, y, and z. All these 3 variables are going to take non-negative integral solutions. What do you mean by non-negative integral solutions? That your x can take any integral solution which is greater than equals to 0. Same thing with y and same thing with z. Now, how many such non-negative integral solutions are there such that your x plus y plus z gives us 8? Now think about it. If I say that your x is taking the value 2, y is taking the value 4, and z is taking the value 2, it is one solution. If it takes 0, 0, 8, it's another solution. If it takes, let us say, 1, 7, and 0, it's another solution. Even if it is 7, 1, and 0, it's another solution, and this thing goes on. So is it not the same way of saying that in how many different ways 8 identical objects can be distributed among 3 heads, x, y, and z? Think about it. I am having 8 identical objects, and we are having 3 groups. Here 3 objects are there, 3 heads are there, which are x, y, and z. So let me just introduce 2 separators, because this 2 separators is going to divide these 8 objects into 3 groups. So the total number of ways in which these 8 objects, identical objects, and these 2 separators can arrange among themselves will give us the total number of solution that this equation can take. Is yes or no? See, if this separator, let us say, if this separator is here, so the solution is 2, 3, and 3. It's a solution. Now, if this separator goes here, so the solution will be 0, 5, and 3. Again, if this separator comes here, so we are having 0, 0, 8, and this thing goes on. So it is same question with a different, it's the same ice cream with a different topping. There are 8 identical coins or 8 identical objects, and there are 2 separators. So total number of ways in which these 8 identical objects and these 2 identical separators can arrange among themselves is what? It's 8 plus 2 factorial divided by 8 objects are identical, so it is divided by factorial 8. And two separators are identical, which is divided by factorial 2. So that gives us factorial 10 divided by factorial 8 into factorial 2, which is same as your 10C2, which can also be written as 8 plus 3 minus 1 C3 minus 1. That is, if there are n identical objects and you have to divide it into R groups, then total number of ways that you can do, as we have learned from the Beggar or partition method, it is n plus R minus 1 CR minus 1 ways. The same thing is applied in this question also. Okay? But one thing we should be very careful. Again and again I'm telling you, you must be careful about that. Whatever values of x, y, z you are taking, that should be without any restrictions. That is, your x, y, z will always take greater than equals to 0, y also the same thing, as well as your z. If this condition prevails, then we can use this partition method or Beggar method at ease. And you see, every problem is becoming so easy the moment we use this partition method or Beggar method. Okay, let me take another problem. See this question. Now there is a problem. Here I cannot use my partition method directly. Because you can understand why. Because there is a restriction in case of y. I told you that you can use the partition method only when there is no restriction. But here for y, there is a restriction. What is the restriction? That y is greater than equals to 1. But you see, partition method or Beggar method is a unique method. It's a wonderful method. And you know, the moment we use partition method, it becomes pretty simple. I mean, the whole complex sum becomes very simple to solve. So what I will try to do here is, I will try to convert this thing mathematically in some form where we can use partition method. Every time we are using partition method, and we will use partition method every time in this type of problem. But how to convert in our comfortable form? That is, there will be no restriction. Check it out. This method is what called your substitution method. This is called substitution method. What is that substitution method? Now it states that, let us say let y is written as 1 plus, let us say k. It means what? We have been given that y is greater than equals to 1. That implies y is greater than equals to 1. That implies your k is greater than equals to 0. Are you getting the point? If y is 1, then k is 0. If y is 2, then k is 1. If y is 3, your k will be 2, and this thing goes on. So this equation, which is given to us like x plus y plus z equals to 8, I can replace this y by using this formula, this substitution. So I can write x plus 1 plus k plus z, that gives us 8. Now which says that x plus k plus z is basically 7. Now to find out the number of non-negative integral solution for this is same as finding out the number of solution of this equation when these given conditions are given. Is it clear? But in this case, observe, your x is greater than equals to 0. That's okay. Here we got that k is also greater than equals to 0 and z is also greater than equals to 0. So now we are free to use the partition method. Is it clear? Therefore, total number of ways will be 7 plus number of variables is 3 minus 1 C3 minus 1. So that gives us 9C2 is your required answer. For this equation, the total number of integral solutions for this equation when this condition x is greater than equals to 0, y is greater than equals to 1 and z is greater than equals to is taking place. Is this clear to all of you? Every time whenever we are going to find out the integral solution of this kind of equations, we will always use partition method. But in that case, we should be very careful that there should not be any restriction. That is, every time we must find out non-negative integral solution. But if some conditions are given to us, with the help of substitution method, we will transform this equation into an equation which has no restriction. Why? Because in that case, we can use the partition method. That's it. Is it clear? Let me take another example. So this question. Here x plus y plus z is 8. X is greater than equals to 0. Here they have given y is greater than 0 and z is greater than 1. What do you mean by that? Integral solutions you want. That is, your y can take any value greater than equals to 1. And z can take any value which is greater than equals to 2. So can we use partition method here? No, because restriction is given to us. So what to do? By using substitution method, what we will say? We will say let y is equals to, let us say 1 plus k1, where k1 is greater than equals to 0. And z is 2 plus k2, where k2 is greater than equals to 0. Are you getting my point? Z is greater than equals to 2, and we have taken z is 2 plus k2, where k2 is greater than equals to 0, fulfills this condition. Okay, so this equation now becomes what? Y is replacing by 1 plus k1, z I am replacing by 2 plus k2, which is equals to 8. That implies x plus k1 plus k2, that gives us 8 minus 3, that gives us 5. Now in this case, we have no restriction. Check it. We have no restriction. And now we are free to use the partition method or Beggar method. In this case, what will be the partition method? Formula we are using? It is n plus r. R is the number of variables. Here the number of variables is 3. So 3 minus 1, C3 minus 1, that gives us 7C2. Is it clear? Now the question is, you can ask me, sir, every time whenever they give us like this question, will I have to substitute and go for this? No. We can use the shortcut method simply by observing this. You see, in the question we have been given x is greater than equals to 0, but y is greater than equals to 1 and z is greater than equals to 2. Now, in the final answer, you see, in the final equation, the transformed equation, what we got? We got this thing is 5. How we got 5? It's basically 8 minus 3. Right? So how we got it? If you want to do it little quickly, if you want to jump some steps, you can remember in this way, whatever it is greater than equals to 1, greater than equals to 2, you simply add these two. That is, y is 1 and z is 2. So total is 3. You simply subtract that 3 from the number which is given to us and then apply the partition method, you are going to get your answer. Let me take an example. Suppose if I say x plus y plus z plus w equals to say 15. And if I say x is greater than equals to 1, y is greater than equals to 0, z is greater than equals to 2, and let us say w is greater than equals to 4. Now, how many such integral solutions are possible from this equation? So all you do is, for a shortcut one, all you will do is, you will simply add 4 plus 2, that is 6, plus 1, that is 7. So you simply write this equation in this way, x plus y plus z plus w equals to 15 minus 7, which gives us 8. And therefore your answer will be 8 plus 4 minus 1. 4 variables are there, that is why it is 4. 4 minus 1, C4 minus 1, that gives us 11C3, and that's your answer. Is it clear to all? So this is the shortcut way you can use. That's it. Okay? Let me take another problem. In this question, we have been said that find the number of non-negative integral solutions of the equation x plus y plus 2z equals to 8. That is, your x is greater than equals to 0, y is greater than equals to 0, and z is greater than equals to 0. But in this case, we cannot use the partition method directly. Because here there is 2z. It's not only z, it's 2z. So in this case, we will consider some cases. Case 1. When your z is 0, then your x plus y becomes 8. In this case, your x is greater than equals to 0 and y is greater than equals to 0. So here I am free to use the partition or Beggar method. And in that case, the total number of solutions that you are going to have is basically 8 plus 2 minus 1, C2 minus 1. That is 9C1. Is it clear? In which all these 9C1, that is 9 ways, your z is 0. And your x and y can take all possible combinations such that their sum is going to give us 8. Now let us consider case 2. If z is 1, in that case your x plus y becomes, actually x plus y is 8 minus 2, that is x plus y is 6. Again, we are free to use our partition method. In this case, the answer will be 6 plus 2 minus 1, C2 minus 1. That is 7C1 ways. Now let us take case 3, where your z is taking 2. Therefore, your x plus y, and this thing becomes 4 equals to 8, implies x plus y is 4. So total number of ways will be 4 plus 2 minus 1, C2 minus 1, that is 5C1 ways. Isn't it so? So this 5C1 or 5 ways, in each solution, your z is going to take the value 2. And the total number of these 5 ways will give us different combinations of x and y, such that when you add them, you are going to get the sum as 4. Okay? So now, case 4. When z is 3, then x plus y becomes 2. Therefore, the total number of ways in this case will be 2 plus 2 minus 1, C2 minus 1. That is 3C1 ways, right? And then we have to take case 5, where your z is coming to 4. If z is 4, your x plus y becomes what? It becomes 0. Okay? So x plus y is 0. That can be done in only one way, because the only combination is x is 0 and y is 0, no other way. If you want to use the partition formula, you can use that. It's 0 plus 2 minus 1, C2 minus 1. That is coming like 1C1, which is your one way, right? Therefore, the total number of ways will be 9C1, that is 9 ways, 7 ways, 5 ways, 3 ways, and 1 way. So it is coming like what? It is coming like, so if you add them, we are going to have 25. Okay? So there are 25 number of non-negative integral solutions are there in this case. In the next, in the next tutorial, I'm going to teach you a new theorem which is called multinomial theorem. When you will learn multinomial theorem, you will find that this kind of problems can be done in a much shorter way. That we will learn in next tutorial, not in this class. So here we have understood, even if there are some scalars multiplied with the variable, there also we can solve it by using partition method, right? Let me take another example. See this question. This question is little bit different. They're saying that find out the number of non-negative integral solutions, but there is a condition. The condition is x plus y plus z is less than equals to 8. Now here we cannot use the partition method directly, because though you have no restrictions in this case, but you don't have a fixed value. The sum of x plus y plus z can be 8, can be anything less than 8 or equals to 8. It can be 7, it can be 6, it can be 5, it can be 8, it can be 0 even. So since there is no fixed number of objects available to us, so we cannot use directly that partition formula. So what to do here? In this case, I'm introducing a dummy variable, let us say k, in such a way that when you add this k, it becomes 8. Now you will say, sir, how it is possible? I will say, yes, it is possible. Why? Because if suppose k is 0, then your x plus y plus z is taking the value 8, which is absolutely perfect for this given condition. If I take k is 1, then you are getting x plus y plus z as 7. Yes, that is also a given condition for this given inequation. Because x plus y plus z is anything less than 8, it can be 7, no problem. If k is 2, then again your x plus y plus z becomes 6. Yes, that is also possible. So this thing goes on. So now, can we say that in this case, in the equation x plus y plus z plus k is 8, in this case, your x is greater than equals to 0, okay, y is greater than equals to 0, z is greater than equals to 0. At the same time, the dummy variable k, that is also greater than or equals to 0. So in this case, now I am free to apply my Beggar's method or the partition method. In this case, the total number of solutions will be 8 plus 4 minus 1 C4 minus 1. That gives us 11 C3, and that will be your answer. Have you understood the problem? The question was, it was less than equals to 8. It means what? Your x plus y plus z can take 8, 7, 6, 5, 4, 3, 2 and 1, as well as it can take 0. Because we want non-negative integral solutions. But in this case, we cannot use partition method. Though we have been given x, y, z are all greater than equals to 0, that is, there is no restriction. But since there are not fixed amount, I mean the fixed number, the number is not fixed. That is, the number of objects is not fixed. We cannot do that. So to make it a fixed number, what we have done, we have used the dummy variable k over here. In this case, your k can take 0, 1, 2, 3, 4 and so on. So accordingly, your dummy variable taking different values, and accordingly we are getting x plus y plus z as some value which is less than or equals to 8. Now the moment we do that, now we are free to use your partition method. That's exactly what I have done here. Is it clear to everyone? Okay, let me take another problem of this kind. See this question. Again, we have to find out some non-negative integral solution for this inequation. But in this case, in the previous case, we have only one boundary. But in this case, we are having two boundaries. So what to do in this case? Okay, so first let us try to solve this one. And then we will talk about the left-hand side boundary. X plus y plus z is less than equals to 12. Let me introduce a dummy variable k here. So x plus y plus z plus k, this is equals to 12. In this case, your k can take any value greater than or equals to 0. So total number of non-negative integral solution for this equation will be 12 plus 4 minus 1, C4 minus 1, that is 15 C3. Are you with me? But now, if suppose k takes the value 8, Then your x plus y plus z, if k takes the value, let us say 8. Then your x plus y plus z becomes 4, but this value I will not take. Yes or no? Because these are the values, the sum of x plus y plus z becomes 4. It means it is less than 6. So I have to eliminate all those possibilities where x plus y plus z becomes less than 6. That is what I want to say. We have to eliminate all the possibilities where x plus y plus z is less than equals to 5. Till 6, it's okay, I will take it. But below 6, I'm not going to take it. So how many number of such non-negative integral solutions possible in this case? Where x, y, z all are greater than equals to 0? In this case, it will be, I will again introduce a dummy variable, let us say w here, which is equals to 5, and w is greater than equals to 0. So total number of such non-negative integral solutions so formed will be 5 plus 4 minus 1 C4 minus 1. So that gives us 8C3. And these 8C3 are the total number of ways in which the sum x plus y plus z is less than equals to 5, which has already been considered in this answer. The values which are less than equals to 5 also considered here. But I don't want that. So what I will do to find out the total number of non-negative integral solution in this given condition, the total number of non-negative integral solution will be 15C3 minus 8C3. Again, I'm not going for the calculation. Calculation you can do by yourself. And that will be your final answer. Are you with me or not? Have you understood this problem or not clearly? So what I have done here, the restriction, in the previous problem, there was only one boundary in the right hand side. But in this problem, we are having two boundaries. It's okay. So what we have done, first we have handled the right hand side boundary and we find out the number of solutions. But here, there will be some solutions which are less than equals to, less than 6. That solutions we don't want. So we have to subtract those possibilities from this answer. So what I've done, I've similarly applied the condition for which this x plus y plus z will be less than equals to 5. We found the total number of non-negative integral solutions we are getting for this inequation. And then we have subtracted those possibilities from the total one to get the number of non-integral solutions lying exactly between 6 and 12. That's it. Is it clear to everyone? Absolutely? Okay. So that's all for today's class. I hope you have enjoyed the topic I have discussed today. So see you very soon in my next video. Till then, stay tuned to us and don't forget to subscribe, like and share this video. Thank you so much. Take a very good care of yourself.